Okay, guys, this is our second video on separable differential equations. In the last one, we covered a little bit of confirming that a given equation is a solution to a given differential equation, and that's just a matter of taking derivatives, plugging in, and being able to, not mess up algebraically. In terms of separable differential equations, the integration is usually not all that difficult. Neither is the separation of the variables. What does need to be taken into account, however, is you just need to be careful about the algebra after the fact. Most of the mistakes are made in the algebra and the manipulation of the variables and solving for y, if indeed you need to solve for y. That's done after the integration. So we'll be careful with that as we move forward, but let's go ahead and just jump right in with another example. Let's say we're asked for the general solution to that one. As per usual, y prime, because I need to break it up, needs to be expressed uh, as a ratio, okay? And then, of course, in order to get y's together and x's together, we just need to do a little bit of division and multiplication. This, of course, winds up being y to the negative 2 dy is equal to 1 minus x squared dx, and that is probably the form that's easiest to do my integration. So I get negative 1 over y is equal to x minus 1/3 x cubed plus c, and then we just need to, we can just multiply through by a negative, and I get 1 over y is equal to 1/3 x cubed minus x plus c, a different c. I mean, if you want to keep track of them, I mean, this was your first c, this is a different c, and then you would just flip it over, okay? And you would get 1 over 1/3 x cubed minus x plus c2. And if you were concerned about the nature of the complex nature of the fraction, you would just multiply it by 3 over 3, and you would wind up getting 1 over x cubed minus 3x, and that would just be a third constant right there, okay? And that would be 1 over x cubed minus 3x plus c3. And the thing is that in terms of, let's see, how many is that? That's 1, 2, 3, 4, 5, 6, 7. That's 8 lines, 7 individual steps. Only one of the steps is calculus, right? It's only going from here to here that's actually calculus. The rest of it is just algebra. It's just manipulation in terms of algebra. So you only have one place to screw up the calculus. You have tons of places to screw up the algebra. Isn't that wonderful? Okay, let's go ahead and move on. A little error right there messed up the fact that I don't have room to do another column on that one, but let's do y times y prime is equal to x. Okay, well, y times dy dx is equal to x, so that winds up being y times dy is equal to x dx. I can integrate both sides on that one. That one seems rather easy. 1/2 y squared is equal to 1/2 x squared plus c. I can go ahead and multiply through by 2 if I want. That would be easy enough. And we'll call that c2. And then you would just subtract. And you would get that. And that is a perfectly legitimate way to leave that. That is actually a hyperbola. Now, here's the thing. We've actually seen this one before because this is just a form of that, isn't it? If I just divide both sides by y right from the get-go, I get back to this. And I've actually seen the slope field for this one, okay? And we should remember back to that one. And we shouldn't be surprised that it turns out to be this. Now, if that constant is negative, then obviously I can multiply through by a negative, and I would get, this would be the difference. A positive versus a negative c2 would be the difference between a vertical and a horizontal hyperbola. Okay. So that differential equation actually satisfies both of those possibilities, and you can actually see that from the slope field, and I think we even discussed that when we saw it. Now, I've done about 4 examples of finding the general solution, so why don't we go ahead and here on this one, let's actually look for a particular solution, or what's oftentimes called an initial value problem. So I have y prime minus 3y plus 12 is equal to 0, and we're going to solve it for y of 2 is equal to 1, which means the ordered pair, 2, 1. Well, this is actually separable. It doesn't really look like it on the face of it, but it actually is, okay? And you can leave the 3 inside of there, or you can factor it out. It really doesn't matter. I would factor it out just because I like, when I'm doing natural log, I like for the coefficient to be 1, but that's just more of a, OCD thing on my part. So what I did is I just turned this into that instead of 3y minus 12. I divided by the y minus 4, multiplied by the dx, and if I'm going to integrate both sides, I get natural log of y minus 4 is equal to 3x plus c. Well, we can go ahead and exponentialize both sides. By the way, again, don't ever use the word exponentialize with anybody else. That's sort of one of my tendency to make up words just because they're really good at expressing what we're actually trying to do. I'm pretty sure that's actually not an official word. Now, e to the c is a constant, right? All I did from here to here was just use rules of exponents, okay? And therefore, we'll pull e to the c out in front, and we'll call it a, since we're used to seeing that, like when we did growth and decay problems. And this is actually just a very straightforward exponential. Okay, 2, 1. Well, if that's the case, 1 is equal to a times e to the 6 plus 4. Then a is, if I subtract 4 from both sides, that winds up being negative 3 over e to the 6, and that's equal to a. Oh, sorry. There you go. Solve for a. And so y is equal to negative 3 e to the 6th e to the 3x plus 4. Okay. Now, of course, this e to the 6 can be combined with that e by rules of exponents, and you can actually wind up getting, 3x minus 6 plus 4, something like that. That winds up being probably a little bit prettier. You really don't want that as a really nasty coefficient. You can sort of take that e to the 6 and make it e to the 3x's denominator, and by rules of exponents, transform it into a difference up in that exponent. But basically, like I said, of all of this, the only thing that was true calculus was from here to here. Okay, you use 2 steps of algebra to basically separate, 1 step of calculus, and then you used rules of exponents, a little bit of algebra, substituting in a little bit of arithmetic, putting it back in as the actual a value, and then a little bit more, rules of exponents in order to get it into a much more aesthetically pleasing form. And that's basically how you do it. I mean, only 1 step of that was actually calculus. The rest of it is algebraic moves, which should be second nature to you by now. If they're not, I'm, of course, sorely disappointed, and I'm, sighing and shaking my head at you right now. Alrighty. Since time is of the essence, we'll go ahead and keep plowing through this, and you get y of 2 is equal to 2. Separation of variables ought to be pretty easy on this one as well. I mean, it rarely is a problem. Oftentimes you have to use a little bit of rules of exponents or properties of logarithms or something like that to sort of, or factoring in order to play with it a little bit. But beyond that, the separation of variables ought to be 1 or 2 steps. It shouldn't really be all that taxing. Okay, get the y's together, get the x's together. Integrate. Natural log of y minus 2 is equal to 1/2 x squared minus x plus c. Let's go ahead and exponentialize both sides. Yep, there I said it again. 1/2 x squared minus x. And we'll go ahead and just, instead of calling that plus c, we'll go ahead and do the rules of exponents and actually call it times e to the c. That, of course, I'm going to transform and call a, since I'm going to move it out in front here and have it be a coefficient. And that winds up being e to the 1/2 x squared minus x with an a out in front plus 2. Now that would be a general solution. That would be the general solution to the given differential equation. But I'm given an initial condition, so I can actually go ahead and plug in. 2 is the output when 2 is the input. Now if I plug in 2, I'm going to get 1/2 of 4, which is 2, minus 2, which is 0. Okay, and therefore I'm going to get 0 is equal to a times 1. What went wrong here? Okay, and therefore a has to be equal to 0. That's really weird. It must be one of those, must be, oh, that's why. That totally makes sense now that I look at it, okay? And here's one of those times when you get an unexpected answer and you might think that you've made a mistake or that the method has failed you, but let's actually think about this for a second. This transforms it into y is equal to 0, e to the 1/2 x squared minus x plus 2, or just y is equal to 2. Now, does that make sense? Well, that is a constant function, which means it has a slope of 0. What happens when you plug 2 into the original differential equation? That factor becomes 0. So it actually does make sense. You went through all of this where actually if you had stopped and thought about it right from the beginning, you could have just said, oh, well, that makes a difference. That plugging a 2 in for y makes the differential equation equal to 0. And therefore, the equation that goes through 2, 2, that satisfies this, just needs to be y is equal to 2. So you could have actually reasoned it out right from the beginning. But notice that the method actually winds up yielding it winds up actually yielding the true answer, although, you know, a little bit more indirectly than you probably would have liked. Okay? I have a couple more problems, but we'll go ahead and do a third video, and I'll do 4 or 5 or whatever problems. Actually, let's do one more on this video, and then I'll save the remaining ones that I have for a third video, and I think that'll sort of round us out. Let's do dy dt is equal to y e to the negative t, and y of 0 is equal to 1. Okay. Well, again, that makes dy over y is equal to e to the negative t dt. Well, if that's the case, when I integrate both sides, I'm going to get the natural log of y, and that makes negative e to the negative t plus c. And if I exponentialize both sides, that winds up being e to the negative e to the negative t times e to the c, which of course I'm going to call a. And so y is equal to a e to the negative e to the negative t. Now, again, that would be the general solution. But of course, I have an initial condition. So I'm going to go ahead and plug in 0 for the input and 1 for the output. E to the negative e to the negative 0. Now, that up here, that right there, e to the negative 0, which is e to the 0, is 1. So that winds up being 1 is equal to a times e to the negative 1, or a is equal to e. So if a is equal to e, then y is equal to e times e to the negative t, and you could just go ahead and combine it into e 1 minus e to the negative t, and that makes it all nice and pretty. Okay? That right there is the particular solution to the given initial value problem. Okay? We'll go ahead and call it quits on this particular video. One more video to sort of round out our understanding of separable differential equations, and then from there, of course, we move on into logistical growth patterns. Bye.